All right, so here we go, party people. So we're into this next unit, I'm calling it Unit 5, and it's mathematics and chemistry, although it's not the first place we've had mathematics. We've had plenty of places to talk about, the gas law concept and so forth. So what we're talking about today is we're using something called analytical chemistry. Analytical chemistry is the idea that through experimental design, through using a scale and a couple of very simple laboratory techniques, we can actually come up with chemical formulas. We can determine the amount of products that will be formed. We can determine chemical reactions. We can predict how much products will be produced, considering how much reactants. A lot of predictions. Analytical chemistry is the ability to write chemical formulas, write chemical compounds, write complete chemical reactions, determining how much of one we need for the other, the ratio of elements in a formula, and all of the above. So it's really the birth of chemistry was done through mathematics once we had some basics down. And the basics we've covered, the mole concept, where we had boxes of hydrogen and oxygen. Let's just write that for a second. You don't have to just watch for a second. So considering this, this all stems from the mole concept. So earlier on, we talked about this, and I'm not going to spend a whole lot of time, but if we had hydrogen gas, and we had 10 liters of hydrogen gas, and that's an ugly container, but it's hydrogen, and then someone figured out, this is Gay-Lussac, I needed twice as much hydrogen gas to react with oxygen gas to make water. So he figured out exactly the volumes that were necessary to make a certain volume of water. And it came out to be 2 equal volumes, or in this case, I'll put 20 liters. So Gay-Lussac found that when I had hydrogen, okay, and they didn't know what the chemical formula was. That's what the analytical chemist found. And I had oxygen, and of course I made water. Gay-Lussac discovered that if I take 20 liters of hydrogen and I took 10 liters of oxygen, it would make 20 liters of water exactly. Twice as much hydrogen as oxygen. Now today we know water is H2O, twice as much hydrogen. It was because of what hypothesis? Do you remember?
2 separate 10 liters.
Yeah, and it's made 20 liters. I could have written this as a box of 20. Okay? But the bottom line is, as long as the gases are under the same conditions of temperature and pressure, what was proportional here? Do you remember? If I have equal volume, in this case I have the same amount of water gas made in volume as hydrogen started with. What do we know? Equal volumes of gases under the same temperature and pressure have equal what? Number of molecules. So what Amadeo Avogadro helped us understand was that being twice the amount of hydrogen and oxygen, we knew this. This was definite. We did this front, backwards. This was done millions of times in other people's labs. It was irrefutable that twice as much hydrogen gas as oxygen produced the same amount of volume as hydrogen you started with. Kind of weird. You think 30 liters of a gas would make 30 liters of the new compound. But somehow they combine. And that's why they call this the law of combining volumes. So what happened was, with Amadeo Avogadro's hypothesis and Gay-Lussac's work, the only way to figure this out was, well, gosh darn it, it must have been that water, okay, had 1 oxygen and 2 H's. But there's only 1 particle here. Amadeo Avogadro said that this represents 1 particle. It combined. So this is 1 particle, but there's 2 volumes. So they must mean if the 20 liters and 20 liters, this must have the same number of particles. So it was determined that, hey, that probably we have this other oxygen here. And we need another 2 H's. Why? Because there's twice as much what? Hydrogen. So notice I have four hydrogens. But I only have 2 particles. 20 liters, 20 liters. I need 2 particles. What 2 particles would give me a total of 4 H's? How can I make 2 particles with a total of 4 H's? Each particle must have what? 2 H's, right. So it must have been, and that we did what? Have an H here, bonded with another H. And notice, look at this, party people. 1 particle in my example is 10 liters. 1 particle is another 10 liters. Equal volumes, equal number of molecules. But the part is that the particle, the molecule, is 2 atoms in this case. The particle here is 3 atoms together. What's missing?
2 O's.
Well, right, but 2 O's stuck together as a, how many particles? That's right, because it has half the volume. Okay, so it's an O2. So give me the red. And that's how it all started, party people. We used, my friends, colorless gases and figured out the chemical reactions. By using Amadeo Avogadro's hypothesis, we were able to what? Figure out these ratios. And, oh, oxygen is no longer just oxygen. It's O2. It's diatomic. Hydrogen is H2. And not only that, party people, we figured out we need what? 2 of them per one of these to make how many waters? 2 waters. And this is the birth of analytical chemistry. And we said, let's pick a volume that equals 1 mole. We picked 22.4 liters because 22.4 liters of hydrogen gave me 2 grams. And if I wanted per 1 gram or per 1 H, a box of H's of 22.4 liters gave me 1 gram. And we were able to build that. That's where it started from. We've taken a break from this. We're going back to analytical chemistry. Now, we're going to use our reference table. Because if you remember, if I had 22.4 liters and it was picked, 22.4 liters, this container right here was the volume they considered. Because listen, I got a 2-to-1 ratio, party people, 2-to-1. Twice as much hydrogen. I can't count them. If I want to do this math, if I want to make water, and I know it's a silly reaction because we don't like to make water, make other things that are more complicated, but if you think about it in the most simplistic terms, I want to make water. I need 2 of these per 1 of these. Well, we can't look at a microscope and see them. We can't count particles, but if we come up with a universal amount, so we picked 22.4 liters, this volume. Why? Because we figured out that a box, this volume of hydrogen, atoms, single atoms, is 1 gram. 1 gram. Now, of course, we know better. A box of 22.4 liters of hydrogen, as diatomically written, is how many grams? There's 2 hydrogens, right? How many moles of hydrogen atoms are in this box? Right, there's 2. Each one is how many grams? 1 from the periodic table. Right. So we picked this size. We figured out that a box of hydrogen is 2 grams. Because it's diatomic, we know that a box of just 1 of them is 1 gram. And when we compared a box of hydrogen to a box of what? Oxygen, this was 32 grams exactly. We picked this size because it gave me 32 grams. We picked 22.4 liters to be that universal amount to compare because it gave me 32 grams. Knowing that oxygen is diatomic, what's the mass per 1 mole of oxygen? 16. There was a 1 to 16 ratio when you compared these boxes. If these boxes, one having oxygen and one having hydrogen, have the same number of particles according to Avogadro's hypothesis, then the box of oxygen is always 16 times more massive. And if you look at the reference table, and we're going to put this all to work here. If you look at the reference table, what does it say in the middle? It says relative atomic masses. Relative, based on each other. What does hydrogen say? Approximately that is atomic mass of 1. But for us, it means that if I've got a box of hydrogen, which we call a mole at STP, it weighs 1 gram because it's the lightest. We made it to 1. And oxygen, being 16 times more massive, got what? Got the 16. Now we know it's diatomic. So if I've got just O in here, if I just have a box of O's, it's what? 16 grams. We know oxygen bonds with itself, so it's 32. So that's where we get that. So let's put this to use. Okay? Let's go to our first table, or our first worksheet. Very simple. Let's go find how many grams it would be to be 1 mole of sodium fluoride. So if I had sodium fluoride, a box of sodium fluoride, don't I have 2 moles of sodium atoms and 1 mole of sulfur in 1 mole of these particles? So really, I want to find how massive this box would be if these were gas molecules, and I know they're ionic, so it's kind of making a stretch here. But if these are gas molecules, at STP, how heavy would the box be? That means how many grams would this equal to be 1 mole? And in 1 mole of this particle, there's 2 moles of sodium. And there's 1 sulfur, right? So if I've got a mole of these particles, everyone understand there's 2 moles of Na? Right. So I pull them apart. And in 1 mole of this, there's 1 mole of sulfur. So what we do is very simple. This is called a formula mass. The mass of the formula. It really tells me how many grams per mole. And here's our first Regents skill. Determine, we've already done this by the way. This is our what? This is our factor in telling how many grams per mole. But they love to ask what the formula mass is. What's the mass of 1 mole? If we had a box of it, if we want a quantity. So here's how I do it. Very neat and organized. Okay? I have, let's make this bigger. I have 1 sodium. I have 1 mole of sodium. 1 times the atomic mass of sodium. So I go find my sodium, up close and personal, getting the date space of sodium. Okay, excuse me. Sodium has a relative atomic mass that means it's 23 times more massive than hydrogen. But it also means that I've got a box of sodium. Woo, box of sodium. All right, it'd be how many grams? 23. How many sodium atoms are in this box if it's Na2S? 2. So we go 2 times and you round that number 23. So, sorry I put a 1 there. Bad Grodsky, good pizza. Whatever that means. Took out a dot too. Taking out dots, taking out things today. 2 sodiums. 2 times, and here's the number, 23. That gives me a 46. In that particle is also a sulfur. 1 sulfur. So in that mole of sodium fluoride, I've got 2 moles of sodium atoms and 1 mole of sulfur. So I go to sulfur. And I have 1 times whatever the mass of 1 mole of sulfur, or 1 box of sulfur. Okay, I know what it is, but you don't. So you're going to have to go, sulfur is a nonmetal. So we go to the land of the smalls. We find sulfur, okay, 32 grams. It's 32 times more massive than hydrogen, but it also means that it's 32 grams per box, per mole, per equivalent. So we go put it back, and we put 1 times 32, and I know my 1 times tables up to high numbers, hope you do. So 1 times 32, put that in your calculator. 32, you guys are quick, okay. You add them together, and you get 8 and 78. The unit is grams per every mole. So my gosh, in chemistry, 78 grams per mole. I think we can all do that. There's no polar, non-polar, the structure, okay? It's just add up the atoms. Now what does it really mean? It means that I'm going to give you a formula, and I want the formula mass, I want the mass of the formula. It really means how many grams would that be if I had 1 mole? Now what do we use 1 mole? We got to use something. In the previous example, I had 2 H's per 1 O. 2 what? Well, we can use these equivalent or fractions of this equivalent now. Okay, now, the only hard part now is when I start having parentheses. Because now you got to figure out how many atoms, how many moles of atoms per this. Okay, so let's go find this. Now, by the way, you'll notice I say formula mass. That's for things that are ionic. When you start having things that are covalently bonded, we call it a molecular mass. It's the same thing. We're not going to call, these are not really molecules. Remember, these are ionic. They're making crystals. So it's the same exact thing. They just use different names for it. But it's the grams per mole. So barium nitrate. So how many bariums do you see? In 1 mole of barium nitrate, how many moles of barium atoms do you have? 1. So 1 Ba. A lot of this in sheeps. Oh, Sour's not here. Okay. 1 times, what's the atomic mass of barium? Let's go find Ba. All right. So barium's a 137. People don't believe me. I believe Cam. All right. There it is. 137. Okay, that means if I have 1 mole of barium in my box, it'd be 137 grams. So we put that in. You can round. The reason why we can round, because it gives us the most abundant isotope. Again, I know my 1 times tables. You may not, so this might amaze some of you. 1 times 37, 137. Okay? Now here comes where it gets a little bit hairy. How many N's do we have here? 1, but there's 2 nitrates. There's 2 of these. So if you don't quite see what's happening here, my friends in chemistry, what you really have is you have a barium plus 2. And don't you have 2 nitrates? Each one -1? That's what that -2, that's what that 2 outside the parentheses means. That means I have 2 of these. So how many N's do I have overall? So this 2 means I have 2 times 1 is 2. How many oxygens? Right, you got to times everything inside because it's multiple ions. So we've got, we have 2 N's. Okay, 2 times the atomic mass of nitrogen when you round it off is 14. Okay, I'm not making that up. Okay, so it lands in the nonmetals. You go to nitrogen at some point. You see it's 14. That's where I'm getting it from. Okay, this numbers are given to you. No big deal. All right, are we liking this stuff so far? 2 times 14. Yes. It's straightforward. I told you it'd be 28. Okay, how many O's do we have? We have 6 oxygens. The hardest part in this process is getting how many atoms in 1 mole. This means, guys, in 1 mole of barium nitrate, there are 6 moles of oxygen atoms. Everybody cool with that? All right, so 6 times, what's the atomic mass of oxygen? 16, so that would be, see what, 6 times 6, 90, 96. Add this together, what do we get here? 261, 6 and 8, 261. And the unit is? Grams per every mole. And my friends in chemistry, if I wanted 2 moles of this per 1 mole, I'd be like twice that number. Yes?
I did it a different way, but I still got the same answer.
How'd you do it?
I did 1 Ba, 1 nitrogen, and then 3 oxygen, and then at the end I just added 14 and 48 for like the.
Okay, so you just you got
times it by 2.
yeah, so you just multiplied this.
Yeah.
You're doing the same thing. I suggest you do it this way because you might forget how many I have to. Clearly I need 6 O's, 2 N's. But you did the same thing, and if you get the right answer, you're doing the same thing. Okay? Just for fun, may not be fun. How many N's would I have here? Right, how many H's? 12. Right, because there's 3 of these. You times that. How many P's? 1. Okay? So this really isn't that difficult, is it? Now, if you were to go to number 3, we would call this a molecular mass. Why? because molecular mass is now dealing with molecules. So here are some synonyms. They call it formula mass, molecular mass, gram formula mass, gram molecular mass. Sometimes it's called gram atomic mass if it's just atoms. But it's always the same thing, grams per 1 mole. So I'll do number 3 fast. Okay, I have 3 N's. 3 times 14. Okay, what we got there? 12. And then 3 times 42. Okay, then I have 12 H's. 12 times the atomic mass of H was 1. Okay, I don't want to amaze you, but that's 12. All right. And then, of course, I have 1P. 1 times 31. If you look it up, it's 31. Okay, again, I don't want to amaze you, but it's 31. Okay, so we get 5. And then we get 85 grams per mole, assuming I made no mistakes. Is that difficult? Except number 3 would be called a molecular mass. Mass per 1 mole of a molecule, because it's covalent. Questions? Pretty straightforward. It totally would be. Okay, you're going to round off these atomic masses to the most common isotope. All right, let's scroll down. Scroll, scroll, scroll. Let's do number 9 together. Ooh! Number 9, you have to have your naming figured out. What does copper 2 mean? What charge am I dealing with copper? I have to build the chemical formula first. What charge is copper? Plus 2. What the heck is a nitrate?
Oh, it's not. Oh, that's in that. What the heck?
Yes, which is table E, and a nitrate is NO3 minus. Now, this whole cluster is -1. Just told me I'm dealing with copper plus 2 because copper has multiple charges. So I need 2 of these, don't I? So the chemical formula, okay, as some of my teachers used to call it, was CuNO3. Now I need 2 of them, right? So I need what? Parentheses 2. Now I have the chemical formula. I have 1 copper. Okay, 1 times, I believe it's 64, right? 64. Or is it 54? 60. Yeah, checking. 2 N's. 2 times 13. 28. And how many? 5, right? Yes, 6 oxygens. 6 times 16 is what, 96? Add that together, what we get? 8 and 4 is 12. 2 and 8 is 18. 6 and 8, 9, 9 and 9 is what, 188? Okay. Grams per mole. And you are, all you gotta do is use a calculator. What's the concepts here? If you've got parentheses, it's how many? So 2 times 1, 2 times, multiply that. If I said to you this Regents question, if I got 1 mole of copper nitrate, how many moles of oxygen atoms do I have? Regents question. If I have 1 mole of copper nitrate, how many moles of oxygen atoms? 6. That's a Regents question. If I have 0.5 moles of copper nitrate, how many moles of oxygen atoms? For every one of these, there's 6, right? So if I have half of these, what's this number? Right. Okay, cool beans. If beans are cool. If they're chilled, I think they're chilled. Now, let's go on to the second skill. I think we've got this down. If you want to practice, you may. The key is posted. Now, let's look at the next skill. The next skill is using the formula of molecular mass. We're going to come up with a percent by mass. Check this out. Sodium nitrate. We need a formula here. Sodium, what charge like to become? Sodium likes to become +1. Nitrate likes to become, what the heck is that? -1. So you crisscross your applesauce, and you get NaNO3. Now watch this question. What is the percent by mass of sodium? Percent by mass. When you do a percent by mass, party people, using a very, very simple formula. Part over total times 100. Percentage. I want to find the percent by mass of sodium, but I'm not giving you any grams. Just given the formula, can you tell me percent by mass? Where can I get grams from? Well, my friends in chemistry, why don't we pick 1 mole? What's the mass per 1 mole? What do we call that? Formula mass. That'll be my total. And let's figure out the part of the sodium. So let's do that. So let's do percent by mass. I don't have anything in front of me, but it's always going to work because a percentage is really a ratio. So let's pretend I have a mole. It'll work for any amount because it is a percentage. So let's do it. Total. How many sodiums? 1 Na. Na. So 1 Na. So that's, I'll give you a break. I'll do this. So keep yourself at 1 times 23. I'm going to amaze you. 23. Okay, we've got how many N's? 1, right? That 3 is for the O. So 1N, 1 times 14. I'm going to amaze you. 14. Then, of course, I got 3 O's. 3 times 16 is 48. 3 plus 7, 7, 5. What do we got? 3, 4, 95?
85.
Yes, 985. Thank you. That's the total. That's my total. That's 85 grams. We're picking what? I'm picking a mole for this to work. So if I had a mole, just using my periodic table, that's my total. Now, what do they ask for? The sodium. What's the mass of the sodium? Of all the sodiums. That's my part. I want that. Times it by 100 to get your percentage. And what do you have, party people? 27%. This means 27% of the entire mass of this compound is due to the sodium. Take your break, come back, try iron 2 oxide.